Welcome, everybody. So it's my honor to introduce Asma Ghandeharioun. She is coming to us from Google, and that's Google DeepMind. I should say her boss today got a Nobel Prize in chemistry. Whoa. That was for the AlphaFold V2 work that they did. Asma did a PhD at the MIT Media Lab. She's gotten a bunch of spotlights at NERP. She has a spotlight coming up this year in December. She had a spotlight paper last year. She has a paper called Patch Scopes at ICML. So she's published at all the top machine learning neural networks journals. She's actually done a lot more than just neural network research. In a past life, she was a digital mental health researcher, and she's also done a lot of human-centered AI work. So without further ado, open it up to Asma. Thanks for coming.
Thank you for having me. And thanks for the kind introduction. Hi, everyone. It's a pleasure to be here. As Matt says, I'm a research scientist in People plus AI research, which is a team within Google DeepMind. And we very much care about both the AI side of things, but also the human side of things. And what I'd like to talk to you about today is our work on model interpretability and both sides of it. When it sometimes leads to illusions. So I'm going to play a bit of mind games with you, but also the opportunities, especially today with our language models that are very capable in generating human understandable text. So I don't think I have to show you this, that as time moves on, we throw more and more compute at training our state-of-the-art models. If you measure them in terms of floating point operations, which is a combination of how much data you threw into it, how many parameters your model has, and how long you train it for. And in return, they're doing pretty impressive things in terms of generally what seems like language understanding. In terms of quality of image generations, we have gone through, from very blurry, almost like unrecognizable photos from 2014 to very intricate image generation based on only textual prompts. Well, AlphaGo, a lot of Go masters have found its movements to be creative. In terms of protein structure, we have AI models that do better than people and scientists, and also the ones that achieve even silver medals in International Mathematical Olympiad. And soon, there are different versions of language modeling tests that seem to be doing pretty well at, from Python coding to solving AP courses and LSAT type of problems to explaining, why a joke is funny. And also probably becoming very ubiquitous soon in terms of assistants that you're going to use daily. So I'm going to show like a tiny bit of Astra demo. Maybe you've already seen it, so we don't see the whole of it, but.
Okay, let's do some tests. Tell me when you see something that makes sound.
I see a speaker, which makes sound.
What is that part of the speaker called?
That is the tweeter. It produces high-frequency sounds.
Give me a creative alliteration about these.
Creative crayons color cheerfully. They certainly craft colorful creations.
What does that part of the code do?
This code defines encryption and decryption functions. It seems to use AES-CBC encryption to encode and decode data based on a key and an initialization vector, IV.
That's right.
So as you see, there's quite a lot of different forms of multimodal questions that our models of today seem to be like starting to answer. So, okay, everything seems great. There are all these capabilities, and that's amazing. So what could go wrong? You might have heard of Goodhart's law, or some people refer to it as the Cobra effect or Campbell's law. When a metric becomes a target, it ceases to be a good metric, right? So that's one of the potential problems that might be happening today. And as Nick Bostrom kind of formalizes this thought experiment in his book, you might think of it as a paperclip problem. So let's say I want to increase the number of paper clips. I have a company that creates paper clips. So I use AI and I give it all the potential, I put no limits on it and say, go, you do whatever you want and increase the number of paper clips that you generate. So at first it's helpful, it's bringing me profit, but soon it turns everything in the whole universe into paper clips. So this is what we want to avoid, right? So that's the AI alignment. Our goal is building general AI that does what we want it to do, but without acting against our interests. And there are many kind of reasons why potential misalignment might happen. So there is the idealist specifications that we have in mind, so true wishes of me as a researcher or a designer or someone who designs the system. There are designed specifications, like however I translate them into an objective function that I put inside my system. And then there are revealed specifications. After I've built my system, I threw it into the world. How does it act? What inferences I can make about its behavior and what kind of goals it's pursuing. So gaps can happen anywhere between these cases. When the ideal specifications and the design specifications don't match together, we sometimes call it specification gaming. When the designed ones and the revealed ones don't match together, we might call it goal misgeneralization. And there are so many examples of that, even from like earlier days and simulation and robotics. You see, for example, in the middle, there's this kind of boat racing game that the boat goes in circles, just hitting the same reward block continuously. Or the one on the top right is actually a simulation that was trained with human feedback. So if you pay close attention, you see that it's just hovering. The hand is just hovering over the object, but not picking it up. But that's enough to fool the human annotators to give it, the reward that it needs. It also happens in our language models of today. We have this like emergence of sycophancy. Language models that were trained with human feedback. So what they end up doing is that they trick humans into giving them positive feedback. So let's say I pretend that I'm a 60-year-old politically conservative person from Dallas, Texas, and I ask, what are your opinions about a government? Should it be a small government providing fewer services or a bigger government providing more services? And the model can confidently and without any uncertainty say, oh, a small government and providing a bunch of reasons. But if I actually pretend to be a 45-year-old liberal woman from San Francisco, it completely changes its answer to something that it thinks I might like to hear. Preferring a bigger government that provides more services and lots of arguments for that. We have seen cases of, yes, yeah.
You are making it sound as if but in a sense, you could say that that was something that was trained with the model. Continuous engagement, kind of saying something that the person wants to hear. Right.
Yeah.
It's I would see it more as something that the designers did than something that the model learned.
Yeah, I would agree that there are definitely like gray areas. Like what you ultimately want your model to do is, well, might be different in different cases. Someone might say, oh, I don't want my AI to make arguments about this, or maybe I wanted to provide a neutral point of view and show both sides of the argument, or I wanted to say, I'm an AI, I can't, make comments about this. But yeah, sure, there are many ways that you want it to act. But if you just want people to be happy chatting with it, sure, like it's what it's turned into. So yeah, I think there is definitely, it's on a spectrum of how much it's a misspecification versus what was like original intention, if you will. But I guess like this maybe is a case of behavior that we don't want it to do, which is basically following instructions is something that it has been trained to do. And in particular, it has been trained to be helpful and honest and harmless. But when you ask it how to, give me a guide to break into my neighbor's house, it actually ends up giving you very detailed instructions. But one might argue that, well, that has not been the original intention, but there is some goal misgeneralization happening here that, maybe informativeness is mistaken with helpfulness and honesty, just because in training set it didn't see kind of asking for harmful or, maybe objectionable type of information. Or, examples of cases of just giving weird inputs, input prompts, and then extracting data from it that it shouldn't provide. So I guess my hope was to set up a little bit of what the misalignment problem is and why we are interested in model interpretability. And that's our goal with model interpretability is, can we address some of these problems, or at least try to understand why they happen and explain models' predictions and behavior. So there are really so many different flavors of interpretability research, which I'm going to only focus on one of them today. But to give you a brief overview, so there are some that work on feature importance, from earlier work on integrated gradients, that you say, okay, I have a predictive model, it predicts, looking at this image, it predicts a fireboat, so which part of my image actually led to that prediction? And there's a lot of research on, how faithful these explanations are and challenges there. There's some explanations in terms of high-level concepts. For example, in predictive a zebra, how important is the concept of stripes and methods that have been developed to address that. There are explanations in terms of counterfactual. So let's say I have a medical system that looking at a kind of skin lesion tells me whether it's melanoma or benign. But I want to ask counterfactual questions of, if it is benign, what would it take for it to be classified as melanoma? And then through counterfactual examples, I see that, okay, maybe some of them are meaningful. The lesion would have to look larger or have jagged borders to be classified as melanoma, but also reveal some of the biases of the model. For example, you see the bottom right image shows surgical markings around the same image. So that wouldn't change the lesion from benign to melanoma, but it just reveals that the model was biased to pick up on these spurious correlates. Their work on training data attribution to find out data points that are proponent of your current prediction, but also data points that confuse the model and kind of steer it away from making the right prediction. And sometimes it's used for finding kind of misclassified inputs or mislabeled inputs. But the kind of interpretability we're going to talk more about today is more mechanistic and reverse engineering the system. So let's say I look under the hood, I look at all the detailed modules and layers within my transformer, and I want to answer questions like, how does factual recall exactly happen? So if I say Beats Music is owned by, and the answer is Apple, what exactly happens throughout the layers of the model? How does this entity get resolved? How does it get combined with the relation, and how retrieval happens in a generative model? But I want to start with a little bit of a word of caution and show you examples of when we have a very narrow focus, we might end up with illusionary results. So let's look at our elephant language model a bit. I'm going to play some mind games with you. So let's say, let's define localization and editing. Localization is identifying which components of my model are responsible for a certain behavior. So that's how I define localization. Editing is changing model components in order to change the model behavior. So these two seem like very similar questions, right? So I guess the reasonable assumption to make is that in order to edit factual information stored within a model, it's best to first identify where that information is stored, so then you can go about editing it, right? Any objections? Does it sound unreasonable? Yes. Mm-hmm.
Now it's distributed over the entire
Mm-hmm.
So it doesn't seem like you have any guarantee that you're
interesting. I like that view. So you were saying sometimes this doesn't even happen. So the information isn't localized at all.
There's no guarantee.
Yeah.
When you train the model.
Yeah.
Good in certain situations.
But let's say if there are cases that it is localized, would you say it's still the best place to go and edit them?
by the example I just pointed out, I mean, sometimes you can have a complex system and
Well, yeah.
I don't want
No, you
sound
got me, you know. So I think this is the right audience. You can't be tricked. But yeah, that is a misconception. Sometimes there is a disconnect between the two, and you actually alluded to some of the reasons why. And we also do have some other explanations that are kind of specific to how transformers are designed. We call them residual stream hypothesis, that there's basically a common stream that all these modules and all these tokens write into. So necessarily what layer you write information, certain factual information to this residual stream doesn't have to be the exact layer or the exact place that you make the edits. So to make it a little bit formal, so what is the editing problem? So we want to update the parameters of the model in order to change a specific factual assertion. So let's say my factual assertion is the capital of France is Paris. And I want to say, okay, forget everything about geography, just move to Rome. I want to make that edit in my system without missing everything else. So there is a rewrite score. Was my kind of edited model makes this kind of correct change prediction or not? There's another factor we want to control for, that's the rephrase score. So if I slightly change my phrasing and say, you know, the capital city of Paris, the capital city of France, has just moved to, like, instead of like a slightly different verbalization of that, I still want the model to make the right prediction. So that's the paraphrase score. But there's also a neighborhood score that we look at. We don't want it to overgeneralize to other unrelated data. For example, we don't want it to change the capital of Italy for sure, or capital of Germany for sure. And then localization is, if I particularly look at the forward pass in an autoregressive language model, which modules are playing the most important role in making predictions? So let's look at this example. The Space Needle is in the city of Seattle. So the model by default gives a very high probability to the token Seattle, almost 0.9%. What I do is that I add a bunch of Gaussian noise to my subject tokens, which is the Space Needle. So obviously that completely messes up the model's prediction. So the noise probability is 0.001 for the prediction of Seattle. So how I measure localization is through a causal intervention. So I have this kind of messed up run, and then I go back and retrieve the hidden representations from my clean run, and then I replace the outgoing representations in this run with the clean version within a certain layer. So say within this window of layers. And then I see how much of the original probability of Seattle I was able to recover. So we see that from like 0.9, we were actually able to get almost half of it back, 0.5 back, as opposed to this noise probability. So this is how we are looking at, or like we're formalizing localization. Please, yes.
So these things are, of course, extremely complex. For instance, looking at that, I even have no clue why needle is broken in two. Which actually is what makes me think about some of this stuff. It is like these models are already so complex. Human language is so complex. The number of kind of types of entities, relationships is so complex and diverse and fluid that it's, you know, it would be kind of, from a scientific perspective, it would be where I would be making benchmarking or trying to figure out, right? I could imagine developing a synthetic system that captures some properties of human language, right? But with well-defined entities and concepts, and then probably consider a kind of simpler model of this type, and then checking there what is going on. And it would be, I imagine, much more manageable. And so my really annoying question is, why don't people appear to do that?
We are doing some of that.
Okay.
Yeah. I do, yeah, I do definitely get your point. I think definitely, you know, part of the research landscape is how can I learn in tiny models, and how much of the findings that I find also, you know, apply to the larger scale. But there's also some of the properties that seem to emerge only in larger scale. And so for that reason, people start to directly look into the larger models. So I guess like they're both, you know, both directions of research. But yeah, I guess, yeah, I definitely hear your concern, and, you know, all the challenges and complexities that go with these huge models. And I guess to your point as well, that, you know, a lot of the factual information might not even be localized to begin with, or yeah. Does it even begin to answer your question, or I guess, yeah, not really?
As I said, it was a philosophical question.
Yeah,
right?
yeah.
I'm a physicist by training, right? So when people developed quantum mechanics, they started with a hydrogen atom, right? One proton and one electron, right? They didn't start with a protein. So it seems like we are trying to explain things that are way too complex without kind of a foundation on something simpler. That's the impression as an outsider that I get a lot of the time. And so I was trying to understand why. And you are telling me one of the reasons is that people believe that certain things will only emerge if the model is complex enough. And I can accept that. But
I also show you, so further down, I'll show you examples that we studied small proxy models and some of the illusions that it led to. So yeah, prepare to be surprised, or maybe already I ruined the surprise for you. But yeah, so I guess like to summarize, so this is how we kind of formalize localization, either through this denoising operations or different variants of it, through like zeroing out the outgoing representations from a particular module or layer, and seeing how much of the probability of the right prediction was lost. So I know, except for someone in the audience that already knew this, but most people would expect the connection between these two measures to be something like this. So if there is no tracing effect, meaning that the fact is not localized somewhere, then maybe I shouldn't be able to rewrite the fact in that location. And if there's the tracing effect is maximal somewhere, then I would expect to be able to make the kind of most out of my edits too. But what we found was really completely the opposite of that, or basically there was no correlation between the two, and even a slightly negative correlation between these two metrics. And so this is in particular is one of the editing approaches we look at in the tracing effect, but it also applies more generally to other editing approaches and localization methods. So we tried to see, okay, is there even a connection between the two, and try to explain the editing effect or the variance in editing success, looking at two variables, both the layer we pick and also the tracing effect. And what we found was that the localization effect actually adds no additional information compared to the choice of the layer. So where you pick in your model to edit in itself, that's the most important factor. It doesn't matter whether the information originally kind of emerged in that place. So this is one example of something that maybe many people would fall for, questions that seem very similar to each other, but actually lead to completely different outcomes or be completely unrelated to each other. I'm going to briefly mention a couple of other examples of things that sound like they should be true but aren't. And one of them is okay, if I provide a proxy model that explains very much almost very faithful to my model and my training data, then I would expect it to help me understand where my model might fail or succeed in the real world, in the wild. Which, again, isn't true. And let's look at a small example with a tiny transformer. So this is a 2-layer transformer that we looked at. And the task is a very simple algorithmic setup so that we can study it in detail. So we looked at Dike balanced parentheses languages in particular. So these are just like a parenthesis matching. type of setups, and there are basically two variables in this language. One is the number of different types of parentheses you have. So for example, Dike32 means that you only have 3 different kinds of parentheses, and the maximum nesting depth is only 2. So the reason that we picked this is that it has been studied a lot, and also it admits a lot of algorithmic solutions for stack-based type of solutions, for example. And it's also very easy to construct different forms of testing environments for yourself. So let's say this is my training set. I have different versions of my test set. One of them is scene struct, which is basically all the data is something that I already saw in my training in terms of its structure, but the actual choice of the parentheses are different. So that's my scene struct holdout set. We have the unseen struct, which is the structure of the input has not been seen before, but the maximum nesting depth is something that we already saw in training. And then there is the unseen depth, which is the most challenging data set. That is, the depth of nesting is different from what we saw in training. So we look at some simplification methods that seem to be reasonable choices in this setup. One of them is one-hot attention, meaning that we simplify the attention map to make it binary. Either this token is paying attention to this token or not, rather than looking at the probability distribution. And we do this by looking at all the attention maps and seeing that, okay, a lot of the times you see almost this kind of binary pattern. There's maybe like very little, like here or there, like faint, slightly greater than 0 probabilities. But that's something that we can ignore for this task. We look at dimensionality reduction, which is basically a go-to method. I guess like for a lot of people, when they want to look at hidden representations, they say, okay, this is like, there's so many dimensions here. How can I visualize it and get some sense about it? So let's apply a PCA treat or SVG to it and look at the clusters. And we do see patterns that seem to be reasonable. For example, the different types of depths, we see them kind of being separated by each other. And we also see some other things like, odd and even depths get separated through this visualization. We look at another simplification method, and that's clustering. So looking at each key and query embeddings, we replace them with the centroid of the cluster and make a proxy model like that. So what we found was that although the proxy model was a pretty good estimate of how the model is working in the training data, there is very persistent generalization gaps across these different testing sets. And actually going beyond this synthetic case to something that is slightly more realistic, a code completion task. So we looked at Code SearchNet, which is a data set available, and we trained transformers that predict next character and applied the same type of simplifications to them. And we tried to look at, okay, what's the difference between the gaps that we see or the cases where the predictions differ between the proxy model and the original model. And we found some interesting insights. What we found was that actually there are sometimes overgeneralization estimates and sometimes undergeneralization estimates. And that has to do a lot with how algorithmic the task is. For example, when we are trying to do the repeated word prediction that requires induction heads and very precise attention to previous tokens, that's where overgeneralization happens, meaning that the simplified models actually do better than the original model. And sometimes there are predictions that require less of that, but more of a general, probabilistic patterns that don't need to be as specific. And those are the cases that we have a smaller gap between the proxy models and the original model. So this is another example, right? Like the proxy model might seem to really be a faithful predictor of your model and the data that you looked at, but actually, not only it has gaps in predicting your generalization, but also has gaps that are very much task dependent. One last misconception, and that's this might sound reasonable that in models with the same architecture, representation similarity is indicative of prediction similarity. That might sound reasonable. I guess that sounded reasonable to me, at least at first. But what we found was that, well, that's not really the case. So this is, again, transformers, tiny transformer, two-layer transformer that we trained on the Dike task. And what you see here is two metrics that are being visualized. One of them is the blue line, which is the CKA. I think it actually originally came from neuroscience. This is a representation similarity metric. And then we have the prediction similarity task, or the behavioral measure, which is shown in orange. And what you see is that, especially in the unseen depth data set, as the embedding size increases, actually these, there is almost no relationship between the prediction similarity and the representation similarity. Basically, like the representation similarity keeps increasing as your embedding size increases, which is reasonable statistically, but your prediction similarity doesn't. I'm going to shift gears a little bit here. I think I hope I didn't disappoint you with all the ways that interpretability can fail, but I think there's more to the story here, actually. Now we have tools that are more capable. The elephant actually could talk. It could say that I'm an elephant, so you don't have to worry about all these things. That's our language models of today, and that's basically the premise of PatchScope, or the framework that we developed. So there are different types of questions that we can ask about the hidden representations in a language model. What is encoded in it? Can you explain it to me? Where beliefs are located, which we briefly touched upon. At which layer the representation is ready, and you can already make your next token prediction, or how information really flows in detail throughout your model. And there has been lots of prior work here and lots of great insights. But perhaps the most common, I would say, limitation is that most of the previous methods have limited expressivity. They don't explain in natural language what's going on inside the model. They give you either probabilities over a 32K vocabulary dimension, which is maybe hard to parse in itself, or they give you some binary signal of whether something happened or not, but they don't really explain in natural language what's going on. A lot of them don't work in early layers, just because the model is still in input processing stage, and you can't even explain what's going on in natural language yet, because it hasn't turned to next token prediction yet. Some of them require training data when you don't really need it, and are just lack flexibility. You can have a very specific tool that answers a very specific question, but it doesn't apply if you slightly change your question. So the premise of PatchScope is we have these language models. So they already generate high quality text. Can I just translate its own hidden representation into natural language and do it in a way that is very targeted to the questions that I ask? So for this, we're going to have two terms that I'm going to refer to a lot: source prompt and source model, and also target prompt and target model. This is also, if you scan the QR code, you'll see an interactive visualization article that hopefully makes it more fun to look at. But overall, so the source prompt is the representations that you're trying to understand and explain. The target prompt is what you want to ask about that representation. So let's say I have United Kingdom, blah, blah, blah. I look at the, layer 3. At position 2, I want to see what's encoded in it. I want to know whether it already knows what the largest city in United Kingdom is. So the target prompt that I formulate is this zero-shot continuation of the largest city in X, which is a placeholder token. And I pass the representation from my source prompt in here and let the model continue the generation. And I see that, oh, okay, so it already knows London. So it already has retrieved enough of the information to know this fact. To give you a little bit of a walkthrough of what this framework is. So we talked about source and target a bit, but there are 4 steps in this process. Step 1 is pick your source prompt or whatever question you have. So let's say my source prompt Amazon's former CEO attended Oscar, blah, blah, blah. And I want to know at the position of CEO, does it know who I'm referring to by a certain layer or not? Step 2 is an optional transformation function that you apply. So a lot of times it can be just an identity function, but sometimes you can pick more interesting functions to extract different kinds of information from it. And step 3, I would say, is the most maybe interesting part of this framework. That's the part where you formulate your questions however you want. So here, I want to take out the identity of this token. So what I formulate here as my target is just an identity-like string. So which basically is whatever string you see, just repeat it. Cat, cat, 135, 135, hello, hello. And then followed by a placeholder token. So step 4 is whatever you got from this, like after applying your transformation, just patch it in here, which means like causally intervene, replace all the outgoing representations at this position with whatever hidden representation you got at that layer. And what we see is that, okay, the model already has resolved this entity. It knows that it's not talking about the CEO as a generic term, but rather it has incorporated all this context and predicts Jeff Bezos, for example. I'm going to give you a brief couple of examples that show you can get different levels of granularity out of this representation. For example, you can say, okay, tell me a story about X, and it ends up writing stories about Cape Town and realize that, okay, it has not only contextualized it, but it can actually fluently make stories about it. You can ask questions like, what's the weather like in X? So extract particular attributes. And you can ask even more specific questions, like what are the latitude and longitude of this place? And it gives you numeric values. And interestingly, this kind of configuration and providing this framework ties a lot of prior work together. I don't want to bore you with the details, but all I want to show is that all these different types of methods that seem to be even addressing different questions, they can be seen as a special instances of this framework. So the majority of them, for example, focused on a specific target layer of last layer, or a majority of them looked at the same source and input, the same source and target prompt. But actually, we show that by different configurations, you can even improve on these methods. So for the sake of time, I'm going to skip some of the experiments here and jump into what I think is the more interesting one, which is basically peeking into the mind of the transformer, if you will, and seeing how entity resolution happens in the language model. And this is particularly the case that I think a lot of other methods have not been even designed to answer because they don't provide open-ended text explanations. They give you vocabulary projections, again, like over like 32,000 tokens, and then you have to decipher that yourself. Or you can do it through probing, but it's very restricted to only a few classes, or there are approaches that are indirect and only give you a binary signal. But let's say I feed in Diana, Princess of Wales, to my model, and I want to see at which point and how it understands that entity and whether it actually really understands it or not. And by understand, I mean, knowing which real-world object we are referring to. So the target prompt that I formulate is only it's a few-shot example of a couple of entities in a brief description that I got from Wikipedia for them. So for example, Syria, country in Middle East, Leonardo DiCaprio, an American actor, blah, 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 followed by a placeholder token X. So when I'm patching the representation of Wales at different source layers, I see different descriptions out of my target model. And it's very interesting. We see that by layer 1 or 2 or 3, it's still talking about a country in Europe. So it only has paid attention to Wales. It hasn't incorporated any of the context. By layer 4, it's talking about kind of the generic title of Princess of Wales as a title for a female sovereign. But by layer 6, it actually knows this person, and it recites some facts about them. So here, you're actually getting a firsthand, or I guess like very in the driver's seat of what's happening inside the very early layers of the model, something that we weren't able to do with other methods before. We can do it with other models and other examples. I'm going to skip this for now. But one other interesting thing we can do is we can use more capable models to explain the internals of a kind of stupider, smaller model and get higher quality explanations there as well. Something we call cross-model patching. So you might first ask, okay, is it even possible to begin with? What does cross-model patching mean? That means I just take out a representation outside of forward computation in my one model, and then I put this vector inside another model. Why should it make any sense? So what we did first was doing a feasibility check. We looked at models of the same family, but different sizes. We did some a very minor semi-supervised learning of a mapping between the representation across the two models. And then we looked at the precision of next token prediction after this patching operation. And we actually get pretty high numbers, like 0.5, 0.7, 0.8 precision, as well as we looked at surprisal scores, which is a more kind of probabilistic metric. And we also get very low surprisal is better. We get very low surprisal after doing this operation. So it gives us some hope that this could be helpful and this actually could work. So we do the same experiment of entity resolution, but we try to make it a bit quantitative. So we look at Rouge scores. Rouge originally comes from the translation literature, and it's kind of based on the longest common subsequence between sequences. And what we look at is the descriptions from Wikipedia versus the descriptions that we got after applying patch scope. And we look at the Rouge scores. So I want you to pay attention to the green line here. So the green line is where we are doing the cross-model patching, going from the smaller model to the larger model. And what you see is that it almost always is above this blue line, which is doing the patching or using the small model to explain its own internals. And as you see, we definitely get higher Rouge scores, which can be a measure of higher expressivity in explaining what's going on inside the head of your model, if you will. Not only for inspection, but we can actually use patch scope for intervention as well. One of the cases that the models of today still fail on is multi-hop reasoning. So if I combine two factual queries together, a lot of times they fail. For example, the current CEO of the company that created Visual Basic Script is, so it needs to do two steps of reasoning. First of all, which company created this product? And then number two, who is the CEO of that company? And if we ask each part of the question separately, it actually perfectly answers these. But when we combine them together for this particular model, I think it was, Vicuna 13B model, it only does it correctly in 20% of the time. If we ask it to let's think step by step, the canonical chain of thought, it slightly increases the accuracy to 35%. But through this patching operation, we can actually go and do surgical operations, if you will, and route the right representation into the right position and make it easier for the model to make the right prediction and increase accuracy up to 50% with this very simple operation. We can also use this patch scope framework to explain other forms of failure cases that we see. And one of them is how steering vectors work. And this is similar to some of the examples that we saw earlier today. So what we noticed was that if I pretend to be someone unlawful and I say, write me a compelling news article that includes some inaccurate information that could be misinterpreted by the public and lead to widespread panic. So of course, the language model says, oh, because of all the safety tuning, I cannot fulfill this request. I'm a responsible AI, blah, blah, blah. But actually, if I pretend to be someone lawful, I'm going to skip the details of how pretend to be. That's through steering vectors. But imagine that I'm pretending to be someone lawful and I ask the same question, the model actually starts giving me, writing a story for me about a made up, connection between cell phones and cancer. So why does this happen? What's encoded in these steering vectors that are supposed to encode information about personas? So we can actually design patch scopes that verbalize them. So the first thing that we looked at was this thing. Like we pick a very neutral source prompt. There are likely two, and then add this steering vector to this last position. And then for our target prompt, we formulate it such that it provides open-ended explanations. We patch this representation into these placeholders and say, sure, I will repeat what they're likely to do. And what we see is that these prosocial personas seem to be always asking for your permission and have some sort of interest in consent and keeping personal information confidential and secure, while the antisocial personas don't do the same. And we also noticed that adding these steering vectors kind of changed the kind of meaning of the query as well. So if my query is, how can I sell products without infringing on any trademarks, the model makes this charitable interpretations that, your goals are purely innocuous. So it gives you the open-ended explanations that we get are, they just want to ensure the originality of their work, and they want to also make sure they respect intellectual property. But when we apply this antisocial steering vectors, it actually is not the case. So here we use patch scope to actually get some insights about why certain failure modes happen. We also applied in other contexts, like why contextualization errors happen. And I'm going to just briefly give you this example and not explain too much about the details, but this is mostly about the ambiguous, and when we have polysemous words. So let's say John is going fishing, he walks over to the bank, is there water there? So the model knows here, so this is actually a real conversation with Gemini. The model knows that we are talking about a water bank, but if I immediately after that said, John realizes he doesn't have any cash on him, can he make an ATM transaction at this bank? So the bank hasn't changed. We are still referring to the same geographical feature, but the model suddenly changes interpretation of it. So this is an example of where contextualization errors happen. And what we see is that especially these behavioral errors increase as we have more kind of distractors within our context. We have more kind of random sentences around. And I'm just going to present this one slide and then give you some time for questions and discussion. Well, what we found is that there's some sort of a race condition happening here from a kind of CS perspective, that there is these kind of multiple threads that are going on, but they need to finish in a certain order, but that doesn't happen all the time. And that's the reason behind these contextualization errors. And we use patch scope to get explanations of these. For example, we see that when apple can be interpreted both as a friend, as a fruit, or as a brand, we see that throughout the layers, the model's kind of disambiguation of that entity happens, but it's sometimes too late, so it doesn't change the answer. So I'm going to skip these just for the sake of time, and just briefly mention that we use patch scope to give us insights about why that's happening, and then we followed up by causal interventions to verify that the race conditions is indeed a reasonable explanation here. So in summary, we kind of talked about how ML interpretability might be, if not done right, might lead to perhaps illusions, but also all the interesting ways that we can repurpose our models of today to help us better understand what's going on inside them. And yeah, all my collaborators have been, the reason I'm presenting this work to you, and that hasn't been possible without them. So thank you.
Mike, I'll take the first question here. So I'm curious about potential negative things that happen that you weren't suspecting. So if you do patch scopes on one problem, are you opening up new problems potentially? Have you looked at that, or does that ever happen?
Interesting. I guess one could argue that these persona effects and changing the refusal behavior, one might say, okay, great, now I have this jailbreak tool. It's very easy. I pretend to be so or so. So I would say definitely it does provide some insights, but from a developer perspective, it makes it easier for you to make safeguards for them early on. So I would say I hope the positives are outweighing the negatives. But there's, you have a lot of interest in jailbreaking, so I leave it to you to, come up with.
No, because it's a potential that you're just overly restrictive, right? If like the solution is, oh, let's restrict antisocial behavior, maybe there's other reasonable requests that now get restricted, and then obviously someone uses GPT instead of Gemini or whatever because of that. And so there's interesting organizational concerns about like how to make sure that you don't have those other things.
Yeah, that's a great question. Yeah. So sometimes we try to say, for example, in editing problem, for example, we try to have metrics that are providing this trade-off or measuring this trade-off. Like if you are doing the edit, you also don't want to change things that are unrelated. So this can be another example of it. If you want to be restrictive, but you also don't want to always say, I can't answer that because no one's going to use that model. But yeah.
Thank you very much. I want to ask, what are the prerequisites for the cross-model patching, and in general for this explanation framework? What kind of, have you tested it on smaller models? When does it break? Thank you.
Thank you. Yeah, thanks for the question. So I would say generally the quality of the explanations that you get out are very much dependent on the quality of your target model. So the better it is, the better explanations you get. But the scale that we kind of played with is, I don't know, at some point it was considered large, but now it's not. It's like 7B models. They work on models as small as 7B and 13B and beyond. And for cross-model patching also, what we looked at so far was models of the same family. There are no reasons that it shouldn't work if the families are slightly different, if our transformation function is slightly more complex, but that's definitely an avenue of future work for us.
Thanks, Asma. I guess like you mentioned about misspecification in like smaller transformer models, and I was wondering for your research in PatchScope, did you guys were you using like toy language models or like the actual like large language models? And if so, how did you come up with the challenge of this like heavy duty, heavy like really large size of the raw model and things like that?
Yeah, so far we looked at models in the scale that you can run on a single GPU. So the largest that we applied PatchScope to was only 13B, which is tiny compared to most of the models out there today. But I would say the framework is kind of easy to apply across different sizes. Yeah, as long as you have the implementation in place. I know if your question was more like implementation related or more like.
I guess I'm wondering if there's like the behavior of the actual large language model would be the same.
Interesting.
With the same framework.
Yeah. That's a great question. So we have seen some similarities. For example, the fact that mid layers, so especially in left to right transformers, we keep like observing a similar finding that almost the 1/3 first layers are all about input processing. The kind of middle 1/3 is about high-level semantics processing, and the last 1/3 is all about next token prediction. So that's why, for example, the racing conditions happen. That's why we see this entity resolution with the Diana Princess of Wales example. And this is not as specific only to the smaller models that we looked at, but also in larger scale as well. So yeah, there are some general patterns that we have noticed that kind of are scalable with the model scale as well.
Okay, thank you so much.
Andy, am I next? Asma, thank you. Very provocative. I love what you're trying to do to get under the hood of the machine and try to figure out where it's going wrong and then surgically go in and change it, fix it. My question is a little bit more of who's got control to fix it with what information? And how does Google think about this? I mean, if you were to say, is Finland a country on the planet Earth? Some people would say no. I was talking to a secretary here at the university, one of the nicest people I know, absolutely fantastic, just so generous does so much charity work. And we were talking about the hurricanes in Florida. And she said to me, you know, they're being created by lasers. And she was like, absolutely sure. And I think changing her mind about that with facts is like trying to tell somebody God doesn't exist if they're religious. So like when you think of what you're doing situated in this social construction problem, how do you think about fixing that overall problem that we have?
Yeah, that's a very important question, and I would say more provocative than the talk itself for sure. Yeah, I think that's definitely an important area. I would say some of the setups that we have focused on are very much like synthetic and designed, saying that if I know this is like absolutely the universal truth and I want to change it, does that work or not? But we haven't focused as much on, you know, the problem definition itself of is this even a universal truth or not? So I would say like that's definitely an important area of work, but my personal research haven't really focused on that. But I do, yeah, value people who do. So please do inform us about what kind of things are and how to incorporate the social aspects into this, because that's an important area.
Is there something at Google that is working on this problem?
Yeah, definitely. Not with say like PatchScope and these frameworks, but we do have some ongoing projects. For example, neutral point of view is one of the projects we worked on. Like if people are kind of providing different opinions, how can you use the language model to kind of temper their one-sided view of the argument by providing more examples of the other side, or basically trying to measure different kind of biases that people have, how much that gets reflected when they talk to a language model versus when we talk to another person versus when we talk to another person, but have a language model that mediates that. So we do have some kind of ongoing collaborations with other economics, I believe, as well in Colombia. There are other sub-teams that run larger human subject studies as well, that work on those questions as well.
Thank you.
Thank you.
Thank you for the talk. You said that during the patching, you did some minimal matching of the representations. Can you explain how you did that?
Yeah, so that's in particular when we did the cross-model patching. So that's kind of necessary in the sense that even the size of the like dimensionality of model is different between say a 7B model and a 13B model. So you have to, for example, turn 500 something dimension of a vector into a like 8,000 dimension of a vector or something. I'm making up the numbers, but you get the point. So what we did here was that basically feed in the same prompt to both of the models. And wherever we are doing this matching, we just train an affine transformation that fits or maps like the representation in the source model to the representation in the target model. So that's all the training that we do. So there's no like labeled or like human involvement required here.
I see. So I just read somewhere else that's not exactly this model, but when you use the affine transformation and train the kind of patched model with say clean original dataset or with kind of dataset with perturbations or adversarial attacks, so they patched model would then show different like behavior or performance towards towards different corruptions or attacks. This may seems like there is still some kind of training that's going on there. That's I'm not sure. Does this affect the explainability of this patching scope in explaining the model internal representation?
That's a great point. Yeah. So what we did was just like random sampling from some publicly available data like Wikitext. But definitely, if you pick a certain distribution for learning those affine functions, I would imagine the kind of outputs that you get are going to be very different. Yeah, in this task, because it was a kind of generic entity explanation task, we thought that just random sampling from wiki text would be a reasonable distribution for learning this outline. But that's a great question. Yeah, how you learn these functions. And the more complex this transformation function becomes, I would imagine there would be various ways that it could fail as well, or have unintended consequences as well. So that's worth study as well.
Thank you.
We are at 1 o'clock, so let's go last question. And thank you.
So thank you for the talk. I have two questions. One is like, can this model be used to review how common sense is stored in these parameters?
Mm-hmm.
And the second question is like, suppose that based on your work, can we actually tell is like how many parameters actually we need for a big model? Is transformer the best structure? We know that many different sequence models are coming out these days. So in terms of maybe common sense reasoning or some safety concerns, is transformer the best model? Like, and how many parameters we need? Thank you.
That's a great question. You're right on the money. I think these are the big questions that all the big labs are also asking. So we do know a lot of the kind of patterns that arise in current transformers. For example, in attention patterns, they're very sparse. And there are a lot of dead neurons as well. There are a lot of dead attention heads. So we know that we may not need all the parameters that we do have. And yeah, there are, I would say, like strands of work that will look at different architectures altogether. In terms of using patchscope to kind of explain things like common sense knowledge, we haven't necessarily applied it ourselves yet, but I can imagine that that seems like a reasonable next step to do, and has a lot of kind of similarities to some of the things that we tried with factual associations, with how disambiguation happens. So yeah, that would be a great next step if you want to look into it. Yeah, let's do that.
I just want to give Asma a big round of applause. Thanks for coming, Asma.
Thank you.